Good? All right, so a couple things up here. Homework 4 is due on Monday, so we'll work on a lot of those problems today, actually. And the lab tomorrow is Group A. It's called Collisions, and it'll be in the same room, S212. I haven't put the lab up there yet in the labs module, but I'll do that tonight, actually. Okay, so you had the test last week. I had a makeup today, so I haven't graded it yet. So as soon as I grade it, I'll let you know, and then I'll give it back to you next week. So next week, Monday, look for the video, no in-person meeting, but I'll make a video. And then Wednesday we'll meet, just like this week, meet here. And then next Thursday, it'll be Group B. So if you're in Group B, you do not meet this Thursday. Only Group A will meet this Thursday. And then next Thursday, Group A has the week off and Group B will meet. Okay, so it's an actual hands-on lab. I think you're going to like it too. It's collision. We run some carts together. They collide. Some of them stick together. Some of them don't. So we'll actually talk about that today. So homework 4 is the last half of chapter 5, so we'll wrap that up today, and then we're going into chapter 9. So remember, we're skipping around a little bit. We do the 1 through 5, and then 9 and 10, and then we go back and do 6, 7, and 8. So the notes in the module are in that order, in the order that we're going to go through the material. Okay? Any questions on this? Okay. Very good. So let's just start off with the homework then. Hopefully I put a video up there Monday. Hopefully you watched that. That's what we're going to be talking about today. The problems that we're going to be talking about today. And this is the first one. It takes the elevator, oops, that you can't see yet. Okay, so this is homework 4. It takes the elevator in a skyscraper 4 seconds to reach its cruising speed of 10 meters per second. We have a 60-kilogram passenger getting aboard on the ground floor. What is the passenger's apparent weight before the elevator starts moving? So by apparent weight, it means if you're standing on a scale, what does the scale read? So if I'm just standing here right now, not moving, normal force is up on me, and the weight from the earth is down. Those are equal to each other, so that's my true weight. Now if I'm accelerating up, the normal force on me up has to be bigger than the weight. And the normal force on me from the scale is the same thing as the normal force on the scale from me. So the scale would actually read more if I'm accelerating up. You can try it too. Get in an elevator, you'll see the needle will do a little bit of a deflection when you first start. That's because the normal force is actually bigger than the weight. Now if you're going up and you're getting close to your destination, you start to slow down, the scale will actually deflect the other way. Okay, so when it says apparent weight, it means what's the scale actually reading? Okay, so let's take a look at this one. Free body diagram will definitely help us with this problem. Okay. So let's see, we took 4 seconds to reach a cruising speed of 10, so we must have started at rest. And then we reach a cruising speed of 10 meters per second. And we have a person whose mass is 60 kilograms. Okay? So really they're asking us, what is the normal force in the first one? So before the elevator even starts moving, this is the free body diagram. Normal force and weight. And those are equal to each other. So this is really the true weight in the first part. Normal force equal to weight. Now remember, the weight is m times g. So 60 kilograms times 9.8. I think that's 588. You'll have to double check that. But 60 times 10 would be 600. But it's a little bit less than that. So if I do 0.2 times 60, I get 12. So I took 600 minus 12 to get 588. Okay? Very good. So this is if you're not moving. What if you're moving at a constant speed? Is the free body diagram any different? What do you think?
The normal force would be greater than the weight.
Well, if you're moving at just say you're already moving at a constant speed. So if you're a constant speed means the acceleration is 0. So this is actually the same free body diagram. So constant speed, the part to get out of that is the acceleration is 0. So it's the same free body diagram. Now you'd already have to be moving for that to happen. And when you're in an elevator, that's really what happens. You're standing there, then you accelerate up to the speed. You don't want to keep accelerating the whole time, just until you get to the cruising speed. And then we have this picture. So part A and part C, it's the same thing. Part C, it says you're moving at your cruising speed here. And how much is the normal force? Well, it's the same thing as the first part. So A and C is the same thing. B is slightly different though. What is the passenger's apparent weight, or in other words, the normal force, when the elevator is speeding up? So for that situation, oh, okay. Okay, good. So for this situation, for part B, the normal force has to be bigger than the weight. And that's where we actually have an acceleration then. Okay. So you could use Newton's second law. Net force is ma. And here's the tricky part. You have to put in the actual forces. Well, normal minus the weight. Right, and then that gives us a net force up. So ma plus the weight gives you the normal force. Okay, well, you know what the weight is. It's 588. We're given the mass. You'll have to figure out the acceleration. But you can do that now because here's the final speed, here's the initial speed, here's the time. Acceleration, final minus initial speed divided by the time. So you have to do a little bit more work. You've got to come up with what the acceleration is. But once you do that, from up here, plug it in down here to get the normal force. Okay? Good. Any questions on that one? All right, so pretty cool. Let's look at the next one here. So here we have a 32 kilogram child slides down a straight slide inclined at 38 degrees above the horizontal. The child is acted on by his weight, in other words, the force of gravity, the normal force from the slide, and kinetic friction. So those are the only forces. And we want to pick the correct free body diagram, right? You've got all these different pictures here. There's 1, 2, 3, 4 different ones for this first part. Okay, so let's just go through them and see if we can figure out what this is. So this one can't be right? The weight is not perpendicular to the surface here. This really should be the normal force, right? That should be the normal force, and then the weight should be where the normal force is. The weight should be straight down. Okay, so if you're sliding down the incline, friction's in the wrong direction here, right? So if you're sliding down, kinetic friction's got to be back the other way, so it can't be that one. All right, this one looks promising. Everything's in the right direction. Let's just look at the last one to make sure. Okay, here's the problem with the last one. The weight should not be at some kind of angle. The weight should be straight down. So it's got to be on my homework, the third one. Okay, and then again, you could hit review here, and it'll take you to the correct chapter, part of the chapter. You can take a look at that. And then part B is how much is the normal force of the slide on the child. Okay, so let me recreate this picture. All right, so here's the incline. Theta, 38 degrees. We know the mass of the child, 32 kilograms. Going to be sliding down this incline, and how much is the normal force? So again, here I'm just going to model the child as a block sliding down. Normal force, kinetic friction, and here's the weight. So remember this weight from what we did before in chapter 4, or chapter 5 rather, has a part here. This is the weight times the sine of theta. This one over here is the weight times the cosine of theta. That's just from doing a little bit of trigonometry to the whole picture. Okay, so weight has to be straight down. We're thinking about this as being the x direction is down the incline, the y direction is perpendicular to the incline. Well, in terms of the y direction, nothing's happening, right? The block, or in this case the child's not flying off the incline, not going through the incline. So the normal force one direction has to be equal to w cosine theta in the other direction. The only acceleration part is actually down the incline. But perpendicular to the incline, we have that. So the normal is the weight times the cosine of theta. And remember, the weight is mg. And then we've got cosine theta. Okay? Good. So that's how you can get the magnitude of this. Very good. Any questions on that one? All right, so far so good. Now there is one bonus one on the homework actually. So when you go through here, number 4, you don't even have to do number 4 if you don't want to. It's a PHYS simulation. I made it a bonus because you have to use, as it says here, it uses Java. So it might be a little bit of a pain to actually do this unless you have that on your computer. In my office, I just saved it and ran it. It worked fine. So again, it's bonus. You don't have to do this one. It's kind of a fun one to do if you do have the time, though. So I'll leave that one for you. Okay, 27 here. 2 workers are sliding a 470 kilogram crate across the floor. One pushes with a force of 400, and the other pulls in the same direction with 290 using a rope. Both forces are horizontal, and we want to know what is the key piece of information. The crate slides at a constant speed. Okay, good. What is the crate's coefficient of kinetic friction? So hopefully you watch the video, you know what that means. I'll give you a little review here. So we've got 2 different kinds of friction. Kinetic friction is when something is rolling, or not rolling, when something is sliding, so it's in motion. So kinetic friction, so this means kinetic friction, the normal force times mu sub k. Now the mu sub k is the coefficient of kinetic friction. Okay? So kinetic friction is more than static friction. So when you watch the video, you saw that. So there's no units with the coefficient of kinetic friction. That's what this problem is asking us. What is the coefficient of kinetic friction? Okay, so you might ask, well, is there just a formula for it? Well, we could use Newton's second law, and then we'll be able to actually solve for it. So we're going to use forces. And then what we're looking for will come about from using Newton's second law. In this problem, though, constant speed means acceleration is 0. It doesn't mean it's not moving, it's moving at a constant speed. So we do have the normal force, mg, we've got a couple of forces this way. One person is pushing, the other is pulling, but they're in the same direction, so I'm just going to write them like this. So those are both to the right. Now if we didn't have any friction, this crate would actually speed up, but it's not speeding up. It's going at a constant amount, so I know how much friction has to be back this way. So it's 400 plus 290, 690. So these people have broken the crate loose. It's moving at a constant speed. That's what we see right now, moving at a constant speed. So we know how much kinetic friction actually is. Now we need to figure out the coefficient of kinetic friction. This is the definition of it right here. So it'll take a couple of steps, but here's how much the frictional force actually is. And I know that's equal to the normal times mu sub k, so I can solve for mu sub k. It's equal to, from this formula, kinetic friction divided by the normal force. And then I know the normal force from the picture has to be equal to mg. Okay, so let's actually put some numbers in here. 690, and then m was the mass of the crate. I didn't write it down here, but it's 470 in my example. And then times 9.8. So if you notice, newtons, kilogram meter per second squared, that's also newtons, so there is no units. And then we can solve for this. I did not bring my calculator today, so you'll have to help me out. 690 divided by the quantity 470 times 9.8. So I'm going to guess it's about 0.15 or something like that, but you'll have to tell me. Oh, good. Excellent. I did not do this beforehand. It's about 1/7 the way I look at it. It's like 700 divided by 5,000. Okay, so that would be 14 over 10,000, or about 0.15. So these coefficients of kinetic friction, in this example, coefficient of static friction, they're always 1 or less. And the coefficient of kinetic friction is less than the coefficient of static friction. It's hard to break something loose, but once it's broken loose, it's a little easier to move it. Okay. Any questions on this one? All right, very good. So we have a truck parked on a 7-degree slope. Okay, 3,500 kilogram truck parked on a 7-degree slope. How big is the frictional force on the truck? Okay, so we're going to have to look at a picture of this. Gravity's trying to pull the truck down the slope. Something's keeping it there. It's the force of static friction that's keeping it from sliding down the slope here. All right, let's draw this one out. So here's some kind of incline. And I'm just going to draw the truck as just a box. And we know theta is 7 degrees. We know the mass of the truck, 3,500 kilograms. So where my wife used to live, her driveway was an incline, and it was pretty steep. So she went to sleep. And then she woke up, it rained, and then it got really cold out. She woke up, and her truck was almost in the street. Luckily, there was a curb here, and that's what stopped it from going in the street. So there was a certain coefficient of static friction when she parked the truck. It rained and then froze, so the coefficient of static friction got less. It wasn't enough to hold up the truck, so the truck actually slowly slid down the driveway. True story. In this one, it's not. This doesn't happen in this example. Here, the forces are balanced and they stay balanced. So let's look at the forces actually. Normal force, weight, just kind of like the other example that we did. Here's static friction. Okay? Actually, in this one, we're just trying to figure out how much is static friction. Question mark. So again, we'll look at this like x and y, like we have been with things on inclines. So static friction is keeping it from sliding down. A part of the weight is pulling it down the incline. So remember, this part is the weight times the sine of theta. The previous example we did, we had weight cosine theta. That was normal force because these were balanced. Here, static friction this way, weight sine theta that way. Those have to be balanced. So the amount of static friction's got to be equal to the weight. So mg sine theta. Okay, so this one we know the mass, 3,500 times 9.8, and then times the sine of 7. So whatever that turns out to be. Somebody wants to plug that in, that would be awesome. And then, let's see. Did you do sine of 7? So this, okay, yeah, that's good. 4,000, and what was it?
4,180.
Okay, 4,180 newtons. Okay, good. Excellent. Anybody else get that? Excellent. Nice job. Thank you. So this is the amount of static friction that we need. Okay, any questions on this one? All right, very good. Let's take a look at one more. We have, in this one, some blocks. Blocks with mass 2, 3, and 4 are lined up in a row on a frictionless table. All three are pushed forward by a 13 Newton force applied to the 2 kilogram block on the end. And how much force does the 3 kilogram exert on the 4 kilogram block? So we've done a similar one before, just not with 3 blocks. So let's take a look at this. So we got 2, 3, and 4. And 13 newtons is applied to this one. This example, there's no friction. And we want to know, in this first part, the force of 3 on 4. So how much force does 3 exert on 4? Let's do the free body diagram of 4, actually, first. So you got the normal force from the ground. Here's the weight. And then we've got what actually gets this one accelerating. There's the normal force from 3 on 4. So these are sort of hard to visualize. I mean, the real outside force is this 13 newtons that's being applied. And that's what really gets the 3 boxes or blocks in this case to move. But if you just look at 4 on its own, you know, what really is getting 4 to move? It's because it's in contact with 3. That's what gets 4 to actually move. So in this problem, they're asking, you know, how much is this? Now that's the only force actually on block 4. I mean, it's in contact with 3. There's no friction. That's the only force that's on block 4. So if I use Newton's second law, I could say the net force is block 4, I'm using a m sub 4 for that, times A. And then the only actual force is the normal from 3 on 4. Okay, so I can figure out what the normal from 3 on 4 is if I know the acceleration. Luckily, if I thought of this as a whole system, I could figure out the acceleration. So let me do this off to the side. So thinking about it as a system, here's 13 newtons. Here's the weight of 2, 3, and 4. And then here's the normal force from the ground. And I could use Newton's second law. Again, there's no friction. This is looking at it as a system. So Newton's second law, mass 2, 3, 4. That's all of them added together, times the acceleration is equal to 13 newtons. So then 13 newtons divided by this total mass. So when I'm doing mass 2, 3, 4, that means the total mass. That's going to be the acceleration of the system. It's the same thing as the acceleration of the individual parts, though. So 13 newtons divided by 9 kilograms. So 1 4/9, like 1.44 or something like that. Okay, good. So this is the acceleration of the system, but it's the same as the individual parts. So you could use this acceleration here, multiply it by mass 4, which is 4. You can get the force from 3 on 4. Okay? It's a little tricky, I think, just visualizing what really is getting 4 to move. Again, it's because it's in contact with 3. All right, any questions on the first part? Let's see what else we have in store. How much force does 3 exert on 2? So how much force, oh, sorry. So part B down here. How much force does 3 exert on 2? Okay, so you got to definitely look at the free body diagram of 2. So without actually doing this one, here's how I would do part B. Do the free body diagram. Let's actually do that part. So this is for block 2. Oh, okay. Normal force, weight on 2. This is for block 2. There's 13 newtons this way. Right, that's the actual outside force that we have, the 13 newtons. And it's being applied to block 2. And then you've got the normal force from 3 onto back the other way. That's what they're actually asking for. So I drew this one bigger than this one because it's accelerating. It's the same acceleration that we just found from the previous part. So, so use Newton's second law. You'll have to do a little bit of algebra, and then you can figure out the normal from 3 on 2. Right? By Newton's second law, I mean this. Let me actually get us started. Net force, mass 2 times A, which you know. Fill in this part, and then I'll do dot, dot, dot. Normal from 3 on 2 is equal to something. Okay? Good. Any questions on that one? So let me just say something about this one, and then we'll get on keep the momentum going today by moving on to something new. So for this one, that you don't see yet, but you will in a second, we have several blocks over here, block A and block B, some ropes here, and there's a lot of different parts for this one, all the way through part D. Same thing, once you start doing this, you know, what is this outside force? Well, they give you the net acceleration, they give you the mass of both ropes, the mass of this. In the first part, think of it as a system. And if you think about it as a system, you can get the outside force F. And then once you have that, you have to just keep working your way down. what is the tension at the end of rope 1? So I would do the free body diagram for A. You know, you got the outside force up, the weight of A down, and then the tension because of 1 down. You know, just go through it like that. Do the free body diagram of A. You'll have to do some algebra, but then you can figure out what they want. Same thing for the next part here. The tension at the top of rope 1. You know, go through the same thing. Do the free body diagrams. Look at the actual forces on the different entities. This will make more sense once you actually start doing it. But you really do have to break it down into little parts like we did for block 2, 3, and 4. Okay? And then this will be the hardest question so far this semester. Okay? So you got the weekend to look at it. We don't meet Monday, but you know, definitely send me an email if you're having problems with it. We can set up a Zoom meeting or however you want to do that. Maybe I'll even make a little separate video for it or something. But I want you to get started on it. Okay? Sounds good? All right. Very good. Somebody should invent a mask like when you smile it changes color or something, because it's hard to tell, right? I think you're having a good time, but I don't know. Okay. All right, so that's homework 4, due next Monday by midnight. Get a good start on it. Send me any questions. So now we move into chapter 9. So by keeping the momentum going, I mean this is the chapter on momentum. So in this chapter, there's 2 distinct kind of problems. There's problems where you have force, mass, velocity, and time, and we could use this impulse idea to solve those problems. And then we also have problems where things collide, where there's no outside force, but there are internal forces. We could use those to solve collision problems. So the lab that Group A does tomorrow involves collisions. Group B will do it the following week. So you probably have some idea what momentum consists of. Something with more mass has more momentum. Something with a higher velocity has more momentum. And it turns out that's what momentum is, mass times velocity. So we were able to use Newton's second law to solve problems. Sometimes it gets really tricky. In this chapter, we'll just come up with another technique to help us solve some problems. This is really misunderstood term sometimes, impulse. It makes you think that it's a short force, right? It's an impulse. I hit something really quickly, that was the impulse. But in physics, it means something different. It's related to force, that's what makes it confusing. But really it means force times time. And it gives you something called change in momentum. So it doesn't mean a short duration force, it means force times time, as you can read down here. Longer lasting, stronger forces deliver a greater impulse. So force times time, that is the impulse, and it gives you the change in momentum. Probably from chapter 4 and 5 you were thinking, shouldn't there be some kind of time component with force? We just keep doing force is equal to m times a. Shouldn't the amount of time the force is applied matter? And it turns out it does, and we'll see how in this chapter. So the impulse force over a certain amount of time can change the ball's momentum, as you can see in this picture. So part of this chapter is something called the impulse momentum theorem. The other part of the chapter, if there's no outside force, the momentum before and after a collision is the same. In other words, it's conserved. And we can do a whole bunch of different sort of problems for collisions. So law of conservation of momentum deals with collisions. So things actually literally striking together or things exploding. Those are internal forces too. That's the second kind of problem in this chapter. So when it says my take on here, let me show you where this whole relationship actually comes from. So let's start with the kinematics equation that we've seen before. Final velocity is equal to initial velocity plus a times t. That's what we did in the first couple of chapters. I can multiply this whole thing through by mass. mv final, mv initial, ma times t. That's legal to do both sides, multiply it by the same thing. Now I know what m times a is, right, from this chapter that we just completed. This is the net force. So let me rewrite this a little bit. I'm putting mv initial over to the left-hand side, and then this is net force times time. Okay, so as I said, momentum, the symbol for momentum is P actually. It's m times v, that's what momentum is. So then I could rewrite this part as final momentum minus initial momentum is equal to force times time. So if you were thinking, well, shouldn't it matter the amount of time a force is applied? Shouldn't that give you something? Well, it does. It gives you the change in momentum. That's what this is, right? Final momentum minus initial momentum. That's the change in momentum. So change in momentum divided by time is the force. Okay? So this is really the first part of the use of momentum, this impulse relationship. Really, that's what this is here. This equation could actually save your life, believe it or not. So say you're in your car and you go from 60 miles per hour to 0. You don't want that to happen quickly. Happening quickly would mean that the time is really small. So for a really small time, for a given change in momentum, you would have a really big force. So you want to make the time of the change in momentum as big as possible. So the larger you can make the time, the smaller the force is going to be. Because the change in momentum, you're going from 60 to nothing, regardless, you want to make the time as big as possible. So cars do that for you. Do you know how do they do that? Any idea? So think safety, right? Because you want to survive a car accident. How could you, what devices in your car make the time larger? Oh, yeah. Airbags, that's a relatively modern invention. Yeah, airbags. Actually, for Rick and I, it's modern. Probably you guys maybe have always had airbags. That's probably true. Airbags, cars didn't even used to have seat belts. Seat belts make the collision time larger. Crumple zones in your car. You could have one of those smart cars hit a wall. You might be safer in that than like a 57 Chevy hitting a wall, right? Even at the same speed. Because there's airbags, crumple zones, side airbags. All these different devices are really made to make T as big as possible and make the average force on you smaller. Good, so if you've ever been in a car accident and used any of these devices, it was really, you were using this equation and you didn't even know it. Okay, now if you're skydiving and your parachute doesn't open, you're going to go from some speed down to nothing. You want to make that time as big as possible too. People have survived different falls from miles up. How did they do it? Well, somehow they made the T as big as possible. So if you see a bunch of trees, head for the trees. And you hit the branches on your way down and make the T part as big as possible. Or maybe you hit a big snowbank. Whatever it is, you want to try to make the time of your collision as large as possible. Okay? So I thought we could watch a video. I'm going to have to fix the lights in a minute so we can actually see it. Are you familiar with the work of William Shatner? The original Captain Kirk. We're not going to watch a Star Trek right now. Okay, let me let's just see how the sound is. I'll have to maybe go back. Does that sound okay or louder? Good? Okay, good. All right, let me adjust the lights a little. Whoops. Maybe I'll just do that because it's not cooperating. Now there's 3 stories. We're only going to watch the first story.
Today the brothers will be cleaning the solo residences at East 66th Street. Over 400 feet of glass. On the roof, the men prepare to launch a platform like this one. It's designed to suspend them on the side of the building as they work. Unknown to them, there is a serious malfunction, and the Moreno brothers are just moments from a terrifying and spectacular accident.
The two window washers were preparing to launch the rig that morning. They got their equipment ready on the roof of the building. So they had a bucket of hot water, they had squeegees, and they had this rig attached to a carriage and it had electric motors that would elevate them and hold them in place.
Photos from that day show the brothers put down their lunches before positioning the platform.
It's approximately 22 feet in length by 2.5 foot wide, and it's designed to carry 2 workers.
Then they swung the rig over the edge of the building and got on the rig.
When the men stepped on the platform immediately gave way.
I saw the commotion. There were a lot of people standing in the street around the building, screaming and pointing.
New York State Safety Inspector Kevin Dillon arrives on the scene and is witness to the carnage.
There was debris all over the place, scattered all over the place. There was blood.
Tragically, 30-year-old Edgar Moreno was killed instantly. But among the wreckage, paramedic Gary Smiley makes an amazing discovery.
We entered the debris field because they had said there was a guy in there. And we started to move a lot of the metal and the debris. When I first saw him, he was in a sitting position. His hands were around his chest. I went to touch him, and he gasped. And that took us aback because then we realized that this gentleman is actually still alive. I can remember myself and the other guys looking up and just saying to ourselves, it can't be. It's just impossible.
With no time wasted, Alcides is rushed to the hospital. The fall has left him with broken ribs and legs and severe spinal injuries. But just 2 weeks later, on Christmas Day,
I don't know what adjective you'd care to use. Unprecedented, extraordinary. If you are a believer in miracles, this would be one.
Alcides gives his wife Rosario the best present she could ever wish for. He speaks for the first time since the accident. He will make an incredible recovery.
I don't know what to tell you. I'm still at all. I'm still in shock.
I've worked as a paramedic in New York City for approximately 25 years, and I've never seen anyone fall from that height before and survive. It's truly amazing.
And I think Alcides has a guardian angel. To fall in excess of over 400 feet, it's just truly amazing. It would be millions and millions and millions to one of the odds of surviving a fall like that. I just can't explain how he could do that.
Okay, even for New York City, this story is. Let's think about this. My single-story house must be what? 15 feet high? Even if I fell off my roof, it could be fatal. So imagine if my house was over 400 feet high. How can someone fall 47 stories and survive? The whole descent would have been over in less than 5 seconds. But during that time, something extraordinary must have happened. But what? So let's try and unravel this seemingly impossible mystery by starting at the top. It's up here that investigators have discovered that the cause of the accident might be the key to understanding how Alcides Moreno survived. According to evidence recovered from the accident scene, the fall was set in motion by 2 simple but deadly events. The first concerned the Moreno brothers themselves.
If the workers had followed all the safety rules and regulations, they would have been attached to their safety ropes and would have been left dangling on the side of the building.
So why weren't the Moreno brothers saved by theirs? Simple. They weren't wearing them. The second crucial event concerned the way the scaffold had been set up. Now, the window washing platform was supported by cables connected to 2 arms overhead. These loops of cables fastened by crimps were the only things securing the rig to the building. And while analyzing photos of the wreckage, U.S. Labor Department official Richard Mendelson discovered just how that rig failed.
Here we see a shot of one of the crimps. So this is a crimp we recovered from the scene, and the crimps are the attachment devices that were supposed to hold that wire rope together.
Amazingly, these two tiny crimps are capable of supporting the full 1,700-pound weight of a window washing platform and its crew if properly fitted.
And what caused the platform ultimately to collapse was the fact that the crimps had not been pushed in enough. Since it wasn't crimped enough, the added weight of the two brothers, the two workers, as soon as they stepped on the platform was enough to cause it to fall.
But, and this is crucial, it's believed both crimps failed nearly simultaneously. That means the platform was more or less horizontal when it fell, and the two men stayed on board as it plummeted to the street below. This is where hard science takes over. Physicist Professor Brian Schwartz has investigated every inch of this fall, and he believes the platform may have contributed to Alcides' survival by slowing the rate of his descent.
It's a very improbable event. If it were to happen again, the likelihood of survival is very, very small. The platform had a total area of 55 square feet, so that presented a fairly wide area, and as a result, the drag force was quite large. That cuts the velocity by about 50 miles an hour.
Okay, let's think about this some more. When objects fall, air resistance pushes up to oppose the force of gravity pulling down. If the men hadn't been on the platform, they would have hit the ground at around 110 miles per hour. But because the force of drag was pushing up against the bottom of the platform they were standing on, they were slowed to around 60 miles per hour. Does that help?
It's better than 110, but 60 miles an hour is still fast enough to really result in usually death.
So the fact that Alcides was still on the platform wasn't enough to save his life during the fall. But what about the landing? In some final split-second twist of fate, could something have broken Alcides' fall enough to save his life? Could the platform have helped him?
The world was once perfect. Then humans disobeyed God, and the connection between...
Here? It's weird but true. High-rise window washer Alcides Moreno survived the seemingly impossible, a 47-story fall from a New York skyscraper. But how? As investigators pored over the evidence, they discovered something even weirder. An incredible series of events in the final split seconds that may have combined to break Alcides' fall.
What we can see here is we can see scrape marks and some damage to a parapet on one of the windows, and then a scrape going down the face of the building. And this is where we believe that the side of the scaffold platform impacted the short building next to it.
No one knows for sure if this impact was the moment that caused Edgar Moreno to be thrown from the platform and killed. One thing, though, is certain. Alcides remained on the platform, with the rate of his descent reduced as he entered the final phase of the accident.
The fall occurred in a certain way in which the sides of the scaffolding hit the buildings there in the alleyway, and as a result, the landing was a lot longer and a lot softer than it would have been had he just hit the ground flat.
After hitting a ledge, the platform struck a low wall opposite, breaking his fall further and causing the platform to react in a crucial way that saves Alcides' life.
When the platform impacted the adjacent building in that short wall, it collapsed into a V. And my understanding is that Alcides was located in that V when the platform collapsed onto itself.
But how would that have saved his life?
Being a big fan of NASCAR and growing up with the family, we've always watched these horrific crashes where the car rolls and burns, and all of a sudden you see a hand go in and releases a seatbelt, and a guy walks away from a crash, and you scratch your head and you say, well, how did he survive that, you know? And this, in my opinion, is exactly how he survived. I believe that the platform created a roll cage and protected his body.
The platform acted like a spring in some sense, that it broke his fall.
Wow, what an irony. The very platform that caused this terrible accident helped protect our city. But that's not all. You see, our city's posture may also have helped save him too.
The force of stopping got distributed over his whole body, so the force on any one part of his body was a lot smaller than it would have been had he hit, let's say, with his head first or feet first.
You had 47 floors worth of cable and rope that was down in the backyard. It was a pretty immense rubble field that he was just, you know, it's as if somebody just placed him in the middle of it, and probably the only, you know, survival position you could have found him in.
It's the last piece to this incredible puzzle. Against odds of millions to one, a bizarre series of events combined to save this window washer's life. Many people believe our city's survival was a miracle. Well, if you think a miracle can be defined as incredibly good luck, they may be right. But it was also combined with the mind-boggling dynamics of simple physics. I like physics.
All right, so it was two things really. Drag force reduced him to 60 miles per hour. Let's see if I can get the lights to work. But that was still not enough. It was making the time of the collision greater at the very end, right? With the scaffolding hitting the sides of the building, making delta T bigger, and therefore the average force smaller. Come on. Doesn't want to cooperate today. Might have to leave it like that. So, okay, all right. There's nobody over there playing a joke on me, is there? No, okay. Believe it or not, this room is relatively new. All right, we're just gonna do that. Okay, good. So by making the delta T larger, the average force was smaller, and the guy was actually able to survive this. So this fall, 10,000 meters, that's way up there, right? Like 5 miles or something like that. So they must have headed for some sort of snowbank or something like that. Maybe it didn't fully open, maybe it was open a little bit. You know, something must have happened for the person to survive that. Okay, good. So that's the one type of problem that we have in this chapter. Make the time larger, make the average force smaller. Any questions or comments on that? Okay, all right, let's continue on then. This was a show called Weird or What? Okay, so this is, let's just do a little bit more with this equation. So the one that you just saw there, change in momentum, force times time. This is the impulse relationship. So the impulse is sometimes called J. So J, change in momentum, force times time, change in momentum, those are all the same thing. So this will be final momentum minus initial momentum, mv final minus mv initial. You could even write it like this way if you want to. So all these different parts are equal to each other. So you can kind of pick out whichever part you need. So how do you know when to use this relationship? Whenever you have mass, velocity, force, and time. This is a clue to think about the impulse relationship. Now when we get to the next chapter, the energy chapter, we'll have mass, velocity, force, and distance. But for now we have this. Now you could generally do these questions with kinematics and Newton's second law. It just takes a lot longer because you've got to use kinematics to maybe figure out the acceleration. Once you do that, then once you have the acceleration, you can use Newton's second law. It just takes a lot longer. Now that we have the impulse relationship, we could do it a lot faster. We could also solve problems where the force is not constant by using the impulse relationship. Okay. Let me say one more thing about this. Good. So this is the one type of problem. Outside force, mass, velocity, force, and time. Now, if the outside force is 0, so if the force is 0 here, then the change in momentum is 0, right? If there is no outside force, it's 0. The change in momentum is 0. So the other kind, if the change in momentum is 0, that means the initial momentum is equal to the final momentum. So these are the collision problems. So the lab that we do this week and next week, depending on your group, uses this idea that the initial momentum is equal to the final momentum. Okay? And really, to be perfectly accurate, I should remind you that this is a vector. So you've got to look at the x direction independent from the y direction. Same thing with all of these. Okay. Very good. So two different kind of genres of problems. This is the beginning of the chapter, and then this is the last part of the chapter. All right, good. Any questions on that? Nice. So here, when kicking a soccer ball, the amount which the ball is compressed is a measure about the magnitude of the force, and you can see from the picture that the force is not constant. Contact begins and the ball gets really compressed, and then contact ends and it's not as compressed. So while this is happening, the force is changing. It's 0, then it becomes a maximum, then it becomes a minimum, but it's not constant. Okay? But it is over a certain amount of time, so we're going to have a change in momentum. Now, if you had a way to actually calculate the area under this curve, this would give you the change in momentum. That's what calculus is actually for. One use of calculus, calculating the area under the curve. So in this class, we don't use calculus. We're going to have to use just algebra. So in a lot of cases, we could estimate what the area is under the curve. Or instead of using the actual force, we could look at it as an average force. So we'll take a look at both ways of doing it. So the area under the curve you see in the bottom is the same as the area that you see in the top one. So this area, the pink here, is the same as this area. This is the maximum force. This is the average force. So the average force over the same amount of time will give you the same change in momentum. So we can do problems like that, looking at just the average force. Same thing though, the area under force versus time graph gives you the change in momentum. So here's something we can take a look at. You've got two 1 kilogram stationary cue balls struck by cue sticks. The cues exert forces as shown. So in the one on the left, large force, short time, that's actually 2 milliseconds. That's what ms means there. The second one, and these aren't drawn to scale, smaller force, but over a greater amount of time. And then which one has the greatest final speed? And this is a voting one, by the way. So they both have the same mass to begin with. We're assuming that they're both starting from rest. You hit the first one with 100 newtons over 2 milliseconds. The other one has a smaller force, but over a greater amount of time. Okay? And then we want to know which one has the greatest final speed. So if you got your voting card, we can take a look at it. So remember what momentum is: mass times velocity. So the change in momentum is the mass times the change in velocity. That's the area under the curve there. Okay, good. Okay, good.